And I got that new guy. Starting off. The question on the board is one of the uniform distribution question. I'm gonna use it for attendance. Tyler, are you studying for actuarial science? The P exam?
Oh, no,
Not yet.
yeah.
This was one of the P exam question, practice questions that I saw online. Right, probably it's the first topic in the actuarial exam. Most students will try to pass one for the go on the job searching after graduation. So we had most of the actuarial science question have the variable that has certain relation. Rarely we have a question that directly only have one variable. So in this question, we have a variable x. X represent the loss for a policy. So X follow a uniform distribution that is 0 to 1,000. So meaning that the loss is uniformly distributed between 0 and 1,000. I imagine that could be, like or repair of a car, so the cost can be less or small within that range. 1,000, the policy has a deductible, so the policy has a deductible D. And the expected payment under the policy is 25% of what it would be with no deductible. Calculate the D, which is how much deductible should we set? So it's actually 25% of the original payment. Okay, so here, oh, I already made a copy of it over here. So basically, we're looking at how do we set up a representation. So how do we turn that from verbal description of the situation to a mathematical calculation? That's something that we can apply our formula. So number one is identify what the initial variable is the loss. So the loss function x, we say is follow uniform distribution. So we say f of x is density for variable x is equal to it's 0 to 1,000 uniformly distributed. So the value will be 1 over 1,000. So the length of the interval is 1,000. This is when x between the 0 and 1,000. That means if the loss is bigger than 1,000, probably are not going to pay it. I guess this is a very artificial model. So if the loss is outside that range, otherwise we have a 0. So then we are trying to suppose the loss follow that model, and we're going to try to figure out appropriate deductible. So the way we set up deductible so that the expected payment under this policy is what it would be with no deductible. So now we're looking at a model for the payment. You can, it's because the word is an expected payment. So if you want to find out expectation of the payment, you first have to have a formula for the payment. So what's the payment? Let's use a Y, letter Y. So the payment is the Y value equal to, so let's think about what the payment would be. Since we have a deductible, then we would pay 0 if the if the loss is less than the deductible. That's the meaning of the deductible. If your loss is lower than the deductible and the insurance company wouldn't pay it. If the loss is higher than the deductible, so if the X is bigger than D, then they will pay. How much do they pay? They only pay the part that's higher than the deductible, right? So the payment will be X minus X is a loss. You don't pay the total loss. You pay X minus the part that's higher than the deductible. Pay it. So let's look at the two different payments. If the loss is uniformly distributed between 0 and 1,000, so the mean for the value would be 500 average payment. The mean, so expected value for the X is, let's try to switch. Expected value for X, E of X is the mean value, which should be in the middle of the 0 and 1,000 is 500. Between 0, 1, and 1,000, the mean value. So that's what you were expecting to pay if there's no payment, right? If there's no deductible. So without deductible, on average, paying 500. Because if you do not have a deductible, the payment will depend on entirely on loss, right? Whatever was a loss, that's whatever you're going to pay. On average, sometimes less, sometimes more, because it's random variable, but on average it's 500. Now, what would be the payment with the deductible? Then you are calculating the expected value for the Y. According to what it says, the expected payment under the policy is 25% of what would be with no deductible. So we're trying to think about what exactly is 25% of the 500. 25% of 500. And that will be 125. So we're saying expected value for y is supposed to be 125. This is going to be the equation we're solving in order to find the d. So the e of y would still be the question that we need to figure out the following. E of y, since y is now a continuous distribution, we're supposed to do integration. So we're going to integrate. You can see there are two parts of the integration. Everywhere else, it will be zero payment. Only when x is bigger than d, then the payment will be x minus d. So you're going to use integration to find the expectation. Discrete case, you would do the summation to find the expectation. But in the continuous case, we would do integration to find the expectation. So it's going to be x is bigger than d, so it's d to infinity. That's x is bigger than d, so d to infinity is what we're gonna. That's integration. We're gonna find the expectation e of y, which really e of this, since the other part is zero. So we're gonna find e of x minus d. Now y essentially is a function of x, so we can just use the function x density. So we're calculating expectation of y, assuming that y is function of x. So we're applying the density function for x in the modeling of any value related to the y. So this calculation will take the x, using the x as our variable, but essentially the integration, change the integration, and then also our integration function already is changing to the expectation of y. This calculation, since fy is this, we're gonna write decimal 0.001. They're the same thing. So this is equal to integration of b to infinity 0.001 and then x minus b and then dx. So that's the integration. We're going to set this equal to 125 for the purpose of solving for d. And if you want to solve this, mathematically speaking, this integration has to be repeated in order to have it done. Right? So we're going to have this equation we're solving that says 125 is equal to integration b to infinity 0.001 x minus b and then dx. So this is what we're calculating. All right. To make the calculation easier, you can do a change of variable like u equal to x minus c. So this will be 0 to infinity. But if you choose not to change the variable, you have to make sure, keep in mind that x minus c should be better to stay as a whole. So applying power rule, maintain the coefficient 0.01. This is going to be x minus d, this is power 1. So according to the power rule, power plus 1. And then divided by 2. All right, so think about backward. If you're trying to find the derivative x minus d to the power 2 over 2, the derivative of this will be that. So this kind of agree with the power. So now we find the antiderivative. All we have to do is put in the equation in it. That would say infinity. It shouldn't be infinity, is it? Its uniform distribution should be 1000. This there's an upper boundary to the uniform distribution. Instead of infinity, 1000. I realize that the infinity in this integration, it will make it diverge. No problem. So this is integration d to infinity. And then if you put in d, b minus d is 0. So at lower bound is really value 0. And that's the whole point as you were integrating. Keep x minus d. So we don't work that lower limit. Upper limit is 1000 minus d. So you can plug in the upper limit to the calculation. 1000 minus d squared. over 2. And then there's 0.01, but at least we finished the integration, this equals 125. From this, we solve the b, that we can start solving for the b. The rest of them are all algebra, now that the equation is complete. We'll look for ways to solve the equation. For example, if you multiply both sides by 2, you have 250, which then equal to 1000 minus e squared times 0.001. And then you can divide both sides by 0.01. That actually is the same thing as multiplied by 1000. Anytime divide as 0.001. If you divide by a really, really small number, you are making your number bigger. On self squared. You put this, and then you're going to square root both sides of the equation, and then you're going to take 1000 minus that value, and that's e value. So this calculation, because the combination of things, so even though uniform distribution is not a complicated distribution to begin with, but we combine with the level and turn it into a kind of like a linear representation. The calculation that actually involved the integration. That was the original idea, and then finish the integration. So for E, right? Hope the explanation works out. You can see with this kind of question does involve a little bit a little twist in the application of uniform distribution. Thank you. Thank you. Yeah. Oh, you don't remember? You don't have your card with you. But what was your answer? Let me fix it after class. It's okay. So at least in the recording, we verify the attendance. Right, so the answer to the question should be 500. Then can double check your calculation. Do you have any homework question you want to talk about? Yes. Yes.
I have several, so we don't have,
No, it's okay.
number 1, 6, 7, and 10.
Okay. Yeah. Six.
Or not 6, 7, 8.
Seven. Okay, well, let me try to remember 1, 7, 8, and 10. I imagine 1 will take a little bit of time, so I will go over the rest and then maybe we go back to 1. All right, so this is number 7, and we already gave it this. You will find the probability and later they 10. So this is the calculation. Doing integration to find the probability. It's a continuous case. Right, so we are going to integrate the density function. It says more than 110, so you integrate from 110 to the upper limit, which is 160. The domain. And we're integrating the density function 160 over 3x squared dx. And that answer should be, we can bring the 160 over 3 to outside the integral. Then we're integrating 110 to 160. 1 over x squared. 1 over x squared is x to the negative 2. Integrate this with power rule, we will have x to the negative 1 power over negative, this negative power negative 2 has to add 1. Then the upper limit and lower limit. So the answer will be 160 over 3 times. This is negative 1 over x. So it's negative 1 over 160 minus negative 1 over 10. That should be the answer. That's negative, negative, make it positive. So that's that. Okay.
Yeah.
So that's question 7. Question 8. Somehow remember we were doing this one last time. Were you in class lesson?
I thought I was gonna make.
All right. The first question was to calculate the K, the integration of the, find the K. Yeah, the integration of density function from, this case is from 52,000 to infinity. The integration of density function should equal 1. So we will apply that to find the K. I think we
If y'all did it, then I'll go back there and look at.
okay. Then question 10. Yeah, last time we did the 11, we did 7 and 8. We didn't do 1, but we did 2 and 3. So 10. For 10, the question for first one is find the probability. If you have the density function, calculation probability will be a integral. So we would integrate the density function from 46 to upper bound. So to answer the first question, we would integrate 46 to, it says x is bigger than x3. And this one was 0 anyways, there's no point, there's no upper bound, x is bigger than 23. So upper bound will be infinity. I'm going to integrate the density 23 over x squared dx. That's really how you calculate the first question. The rest is all integration. The second question is to find the cumulative distribution function. Cumulative distribution function is the integration of the density function. If you integrate, then CDF has a tendency, which is the increasing function, you start from 0, keep increasing until it's 1, because f of x is probability, right? Probability, when the value is small, probability is 0, when the value is bigger, probability is equal to 1. So the beginning part, this is 0, because at x is less than -3, the density function equals 0, so the CDF will also be 0. So the first one is already 0. The second one, we were supposed to find the probability. So we go by the definition f of x. It is really a probability of that the variable x is less than the number x. So it's less than x, so you're going to integrate your upper limit being the x, and your lower limit would be the 23. So it's 23 to x. So integration we are integrating the density function has variable x. We change the variable, so we put a confliction variable to 23 over t squared dt. So switch the variable t just so we will have x here, and x. If x is your limit value for the integration, then your x cannot be the variable value integration. So then this how it looks like, and then you bring the 23 to the outside, find the antiderivative of 1 over t squared. It will be t to the negative 1 power of negative 1. Write it in the division is negative 1 over t. That's antiderivative. We're going to put it in the integration x at 23 would be the integration limit. Putting the 23 at negative 23 over x. Putting the lower limit would be 23 negative 1 over 23, which is negative 1. Lower limit minus 1, that's positive, right? Minus negative positive 1 minus 23 over x. Okay, any questions so far? When I put in the 23, 1 over 23 times 23, that was negative 1, but you minus negative. That's a lower limit now. This is like value. So going back here, the first question I didn't finish the integration. I'm gonna finish this. That's 0, and this is 1. X 2, 3. Right. Thank you. So it should be 23. And having the density function also made us easy to do the rest of the calculation. So density function really is a probability. For example, if you're going to calculate probability x is bigger than 26, the density function, the cumulative distribution function gives you probability to be lower than a certain number. So if you plug in 46 over here, you'll be getting 1 minus 23 over 46. That's probability to be below 46. To be higher than 46, you do 1 minus that. Right, which will cancel the 1 minus part. So the answer here will be 23 over 46. So we can actually apply the FX, the CDF in the second question to answer the first question, because essentially they're both integrations. So the integration that you did for this one will be similar to the integration that you did for this one, except this one has variable, this one has actual number. Last question, but okay, at least 1 of 4 devices will function for at least 49 months. Now, to function at least 49 months, that's probability x is more than at least 49, more than 49. Right? For that one, it's similar for the first question. This probability for one device, it will be 23 over 49. Because my answer to the first question is 23 over 46. So for one of them to last that long, it's 23 over 49. So we're saying at least 1 out of 4 will last that long. That's not everyone lasts that long. Is some of them last that long, right? At least one. So to calculate at least one, we should calculate the opposite, right? The opposite of at least one of them lasts 49 months long is none of them last at least 49 months long, right? So we calculate the opposite. If they didn't last 49 months long, it's 1 minus. We would follow the CDF. That's the probability for one device to last lower than 49. And then we're talking about 4 devices lasted, all of them lasted below 49. So this, if it's 4 devices, you would raise them to the power 4. This is probably all 4 of them last less than 49. But we're saying opposite of this, right? Well, at least one of them lasts longer than this. So opposite of all of them last less than enough time, you will do 1 minus over there. So we have to think about the logic opposite. We did a logic opposite in that one minus. We also did another logic opposite for A minus. I hope that was okay. So that was the question 10. So for the other one, we did a video last time ago. We should also look at the question number 1 that was slightly harder than the rest because we have to think about the relation. Yeah, I was thinking about, yeah, we're talking about moving this, right? This one has 2 persons and every person's behavior follow a uniform distribution, right? Because, so we have to set up the model to look at the interaction between the 2 variables. It's one of the chapter 8 question. I was gonna move it to chapter 4 to get to move it. Let's see if I already have it there. In chapter 4, we'll look at 2 variables, how they relate to each other. And these are 2 variables. Change this over. So I don't forget. Last time I see, I was gonna move it, but I forget to do it. Right, so I actually copy it into section 4.4. So now we can remove it from the current section. There. This question should be completed in the label. Right, so now there's only relabel. That's fine. So that question, I think the reason that you find it hard about probably because we haven't really talked. Any other questions? We okay?
Yeah.
Right, try the rest. If you still have questions, we can review them. The 7, 8. Okay. So any other questions? All right, today I was going to try to go over a 3.3. So in 3.3, we actually talk about 3 special distribution. I actually have a new file made for them. So in 3.3, we're talking about continuous distribution that's related to Poisson distribution. So all 3, exponential distribution, gamma distribution, and chi-square distribution, the original definition of them is related to Poisson distribution. But once we had the formula, once we have the model, we actually apply this model to model other stuff, not just the one related to exponential distribution. The original idea there. All right, little review there. Basically, we're using exponential distribution to model a waiting time for Poisson distribution. Assuming that you have a Poisson distribution that is has a mean 0 of lambda. So the Poisson distribution, the waiting time, so let's say if x equal n, we have a probability of lambda to the power n over n factorial times e to the negative lambda. All right, so then let's use waiting time. W is represent the waiting time for the first occurrence of the Poisson distribution. In that sense, we tried this before, the waiting time to be less than x. And to be less than x is the opposite waiting more than x. If the waiting time is more than x, that means between 0 and x, 0 occurrence. For probability of 0 occurrence in the Poisson distribution, e to the negative lambda. In our case, the lambda is a mean number occurrence, right? Which related to the time interval. Right now, our time interval is 0 to x. So lambda times x is the actual lambda for the Poisson distribution. So that was the exponential distribution, the probability, the CDF. So once we get our CDF and the derivative of the CDF is our PDF, the density functions. That's the density. So you must should review what we're talking about before. So we're going to devise this notation called sigma, theta. Theta represents the average waiting time, which equal to 1 over lambda. And then with that, we change our exponential distribution formula to 1 over theta times e to the negative x over theta. So if we now have the CDF and the PDF, for example, let's say we want to calculate probability x less than 80, less than 18, assuming the mean for 20. So how do you calculate that? You have CDF and PDF. For the CDF, you go 1 minus e to the negative 18, x is 18 over 20, the theta is 20. So we should know how to apply the CDF or PDF to do some calculation, right? So these are the calculations. You can also use the density function. We integrate the density function from 0 to 18, which allows you to do calculation. Or you can simply plug in theta with the CDF, right? 1 minus e to the negative 18, 20. Same calculation. This integration equal the CDF, which equals the value, which is the same. All right, so this is a picture of the PDF on the left, the CDF on the right, the cumulative distribution function. Now, for exponential distribution, you've got to calculate probably the variable larger than a certain value. You do 1 minus the CDF, but the CDF has 1 minus already. The 1 cancels back to the negative x over theta. So we actually have a shorter way to calculate the value, the probability value for B to be bigger than the number. Couple of examples that we had in this section. Right, this is the question about the waiting time. If you have a average waiting, average lambda equal to 20 per hour, then the lambda equal to 1 over 60 over 20, 20 over 60, which is 1 over third. So I have lambda for the Poisson distribution, therefore theta equal to 3, which means the average 3 minutes. The waiting time is average waiting for 3 minutes. On average, you might have the first occurrence. So 20 customer per hour. So the waiting time for one customer is 3 minutes. That's how we come up with the understanding of the theta and lambda. Right, so we now have a density function. Using the density function, if you want to calculate probably x bigger than 5, you integrate back to infinity of the density function. Density function, the exponential distribution is easier to integrate because the derivative exponential function is exponential function, so we can figure out how to calculate it. Another way to look at this probability to be bigger than number in exponential distribution is e to the x over theta for that. That's so if you go directly from here to here, faster, and that's based on that formula, that conclusion, right? The exponential distribution on the right end is actually not that difficult to calculate, and we can calculate the mean waiting time, the median waiting time, the median waiting time. This is applying the formula with say this picture -5 ln negative theta times ln 0.5. That was we come up with that formula. This is negative theta equals 3 times L/5. We get the median time. Any question? The reason we want to calculate that is to realize the median and mean are not the same time, same thing. In the exponential distribution, the mean waiting time, the average waiting time was 3. But then you see the median, is 2%. We've done this calculation before. This is a MGF for the exponential distribution, moment generating function for exponential distribution. We're gonna have to add e to the tx multiplied with density, and then combine the exponential function with 0 to infinity. We're getting this 1 over 1 minus theta t. Moment generating function. And again, whenever you see that format 1 over 1 minus a number times t, that will always be a moment generating function for exponential distribution. Finding the derivative and the second derivative of the MGF, where it would be and variance, turns out they're closely related. When you say that it's theta squared. Any question? So gamma distribution. Gamma distribution is the waiting time until the ops occurs in. So same with still the Poisson distribution. We're waiting for more than one occurrence. Alpha is the number of occurrence we're waiting for. So the waiting time we come up with this formula. The probability for the waiting time will be less than W is 1 minus waiting time. Bigger than W, if the waiting time is more than W, that means that within the time frame 0 to W, the occurrence, the number of occurrence is less than alpha. We're waiting for the alpha. So that summation is what we're calculating. Again, this because alpha is abstract, so we don't have a set formula for the summation. So instead, we try to find the derivative. We mentioned this before in the derivative computation. They are in applying the product rule. That's what will come up. What's giving us a subtraction. And then many terms in this summation will be canceled. We are left with the first term and the last term. So all the middle term will cancel out because they have opposite signs. So with that, we even cancel what's in the first term, this what's in class. These two cancel also. Then we have one thing left, that's the density function. So in this density function, we have a polynomial. We also have exponential function, and also coefficient of them reminded us of the gamma function, right? So we written down some of the terms. This is my derivation of how they relate to the exponential distribution. We decided to change our notation. Instead of using lambda, which is related to Poisson distribution, we use theta, which is related to waiting time, average waiting time. Theta, so now that's W over theta. And then this lambda replaced by 1 over theta. That lambda replaced as well, so that we have alpha of the 1 over theta, split to the power alpha. And then the denominator alpha minus 1 is being converted to gamma alpha. So then the reason we changed the factorial notation to gamma alpha, part of the reason is factorial calculation only works if alpha is integer, right? But the density function eventually are applied to more scenario than alpha being integer. Alpha can be a fraction like 1/2, 3/2, 3/4. So it's possible for alpha to be a non-integer. And once we convert it to a gamma function, it makes the density function itself more applicable. So that's a little review of gamma distribution. We define gamma t, and here we define some special value, gamma 1 and gamma n. Basically, when gamma function with a variable equal to an integer, what you see is really factorial calculation. This process can be proved. So down here are the proof of it. Any question? We'll review. And you can see the reason that we are using gamma function, gamma as a distribution name is y to the t minus 1 e to the negative 1. You see exactly the same thing in our density function. This is e to the negative t. And here is the polynomial. So this is all the reason there. And also, if you integrate this, W over theta, there's W over theta. If you change your variable, integration of this from 0 to infinity will be the gamma alpha itself, right? With the change of variable. So the denominator will be, after the integration is done, the numerator will both equal to gamma alpha. That's why the whole integration of the density function will actually equal to 1. So everything will come together, and that's kind of the reason why we feel like gamma will be an appropriate name for the distribution. All right, so a little summary of all the things we mentioned. We have our density function now. This is a moment-generating function. It's a power alpha of the exponential distribution moment-generating function. The mean of the gamma function, gamma distribution, mean is alpha times theta. The variance is alpha times theta squared. So they all behave like a couple. The summation of a couple exponential distribution is giving a gamma distribution. So between exponential distribution, waiting time for one Poisson distribution and gamma distribution, waiting time for a couple of Poisson distribution occurrence, they have this additive property. Summation of several exponential distribution is giving us gamma distribution, which is why their mean, their variance, all have that additive property. Any question? Assuming they're independent from each other. Okay, this is a graph, the density function for different value of alpha and theta. As an example, we apply different alpha and theta to answer the question. All right, chi-square distribution. As we mentioned before last time, chi-square distribution is a special case of the gamma distribution. What's special is the theta and alpha that we mentioned in the gamma distribution. Theta was the waiting time, average waiting time for one exponential distribution. Now we purposely made theta equal to 2. And that's really, really special, really different than the other case. Before, theta is free. It's supposed to be the actual waiting time. When we are looking at chi-square distribution, it's no longer the case. So we're just saying theta got equal to 2 of anything. Okay, could be 2 minutes, could be 2 hours, could be 2 of some other interval. We can actually identify, change our time frame to fit. So then the theta actually equal to whatever model you're using. And alpha equal to r over 2. When we do this, one of the benefit is that you multiply theta with alpha, 2 times r over 2 equal to r. So the mean for a chi-square distribution equal to r. Mean equal to r, and then the variance equal to alpha times theta squared. Theta is 2, so 2 squared 4, r over 2 times 4, that's 2r. So chi-square distribution may be the only distribution where the mean double, that's the variance. There's double, and that's one of the things that we watch out for when you're determining what kind of distribution is this, right? You might want to calculate the statistics. What's the mean? What's the variance? And so what kind of relation do they have? Okay. So chi-square distribution has only one parameter because we basically remove the theta, right? Theta is 2, r alpha equal to r over 2, they multiply equal to r. So we are combining theta and alpha, which was a 2 variable, 2 parameter distribution from the gamma distribution into one. In chi-square distribution, there's only one variable, one parameter. Parameter is r. We give it the r special name we call degree of freedom. So r is the degree of freedom for the chi-square distribution. The mean is r, the variance is 2r, and everything is related to the r. Any question? And we have, right, and then I guess that's another reason that I want to use this new file. I'm trying to insert a little bit of the coding with R. That's what I was using. I don't know if it still works. We can run our code online, so you can, if you are okay with installing new software on your computer, I do recommend install R software and then install the R Studio so that you have a computation power with your own computer. But if you don't want to crowd your computer with more software, you can do it online. So for example, here, let's see if it still works. See, run R code online. So this looks as it still works. Well, at one occasion or another, sometimes this thing that still works. There's a server behind it. Sometimes it went offline, but it still works. So we can use this software to do our computation rather than use our table. And for example, we can run this. Make the degree freedom the R equal to 7, and that oversees it. Right. So this is the language to talk to the computer. Right. So I define the freedom, degree freedom equal to 7, you can just write R equal to 7, whatever name you want to give it. So now the word free have a value, which is equal to 7. The function name is called chi-square. The chi-square is the name of the distribution, and we put a word Q to take the one of the quartile. All right, so if you draw a distribution curve, this is our x variable. All right, this is a 0. Chi-square distribution, most of them are positive. So what do we mean if you want to say Q chi-square? Right, you're trying to find in the chi-square distribution. It's, let's say we want to find, we can see the 0.99. 99% will be on the left. Whenever you see a percentage here, most of the time, the in default is cumulative unless you specify otherwise. Like the lower tail equal to true. Meaning that the lower percentage is 99%, and I want to find that font type. That's why we have Q. I want to find on the number line from 0 to infinity what this number is. And then we're gonna have a degree freedom that was make R equal to 7. Find 0.99%, and with that number, that's separate the 99% lower percentage from the upper 99%. So you can almost imagine, since the mean is 7, right here in the middle was 7. I think that number should be higher than 7, theoretically, right? Okay, so we can run this, and then this is just saying, if you want to explain your language, that's it. That's why I prefer how to use R than your statement and will to find percentile of the given probability. So we'll find probability of 0.99% percentile. So we're trying to find 99 percentile in the degree freedom R chi-square curve. Run this, it'll give you a number. Right, that's 18.475. That was, and obviously that's way bigger than 7. Because it's 99% higher. You can certainly find the same thing from the table. Bring the table. Degree freedom 7. You see, degree freedom equal to 7, and we're going to go 99%. This table only shows you the right percent. That was the right side 99, right? You want a cumulative 99. The right tail should be 0.01, 18.475. Okay, so you have to realize R is different than most of the chi-square table. Most of the chi-square table, the percentage we're given is the right tail percentage. And that would really weight the tail on the right side. But R tends to write, if you don't change it, R always present the percentage to the cumulative percentage. On the left. You can never change this. For example, I guess we can change the lower tail to be false. And then that would give you a completely different number. Okay. That means we are 0.99 chi-square curve, and we're looking at upper tail. And you can see 1.239, which exactly it was in the table. 0.99 and 1.239. That's so you can see the chi-square table are giving us the same answer as you would find in R. I guess one of the reasons I want to use R is that I have that freedom to don't worry about the searching the table. So I just tell the computer, give me this R or that R. Identify degree freedom, identify which percentage you're looking at, and then they give you the so this, I'm just trying to explain how do you do it. This is the P Q chi-square. There's a P chi-square. P as in probability. So maybe you have a number that was 5 and degree freedom equal to 7. So I change the name, degree freedom equal to 7, and then now that DF is the same DF as degree freedom equal to 7. If you have a little bit of experience with programming, this is kind of the like sentence by sentence language to tell the computers is what I do. So they do have some connection with the first sentence and second sentence. So first you say degree freedom equals 7, DF equals 7, and then P chi-square 5 greater than or equal to BF. Now you can change it, right? If you phrase it this way, you can change that 7 to a 9 or 10, and then everything else will still be why we would put in multiple sentences, because we're hoping that the same thing can be applied for other situations. If you just directly put P chi-square 5 greater than or equal to 7, and that can only be applied for one situation. So anyway, this is finding probability. Any R language says start with a P, calculate probability for you. Any R that has Q, calculate quantile for you. And like we have Q norm, P norm, which calculate probability in normal distribution. We have QT, PT, which calculate T distributions. So I think R itself is, once you figure out what the naming, the rule for the naming, and how to talk to the computer, it does calculation a lot faster than going through the tables. Any question? So these are a couple of examples using the R. You can definitely change the statement lower tail equal to true or lower tail equal to false to identify you're calculating the left tail or right tail. Using the language. It's the same things. All right, so this is one of the examples in the textbook. The question wants us to find, suppose X is a chi-square distribution. Notation chi-square distribution with a degree of freedom 7, so we start using notation. Find the two constants A and B such that probability for X to be between A and B equal to 0.95. Essentially, we're trying to find the boundary for the middle 95% in the chi-square curve. So how do we do it? We can, if the middle is 95, that means the left side is 0.5 divided by 2.25%, right? 2.25 either percentage. So what we're gonna do is we're gonna find the central percentage, which is 95, and the tail percentage will be alpha equal to 1 minus 0.95, which is 0.05. And then alpha divided by 2 is 0.025, the left tail and right tail. So then now we know we want to know those percentage corresponding to what's the fault time. So we're going to use a Q chi-square in this. You can use a table, right? That's 0.975 and 0.25 degree freedom with 7. So we look at degree freedom 7, 975 is 1.69. And 0.025 is 16.013. So that's going to be our A and B. So A and B is going to be 16 point. That's going to be, is it the same? Yeah, 16.01 for the upper bound, and lower bound is 0.975, 1.69. And I was using R. This is what you see on the table. I use R, you have the same thing. You can say Q chi-square 0.975 greater than equal to 7, lower tail equal to 2, and you see the 1.69. And the other one is when you have the degree, the percentage is 0.025 to find the upper bound. Any question? This is how we use R or use a table. Either one, I would recommend being able to do both. But if you figure out one way to treat this kind of problem, it's okay. That's how the text is done. All right. I would say picture for degree freedom equal to 5. We can identify the percentage. Probably to the right is this one. Any question? This is really trying to understand the chi-square table. On the chi-square table, we enter a number right next to the chi-square notation. That number should represent what's on the right side. Right side of the quantity. X. Okay, so this is an example on 3.2. Question 9 says customer arrive at a shop on average of 30 per hour, which follow to the number current followed for some distribution. So then this is basically for the for some distribution and labeled 30 per hour. So what is the probability that the shopkeeper will have to wait longer than 9.390 minutes for the first 9 customers to arrive? So we're not saying waiting for 1 customer, we're waiting for 9 customers. So that in this case, the alpha equal to, so we're using chi-square now. All right, average of number customer is 30 per hour. So what's the average waiting time? 16 minutes per hour, 30 customer per hour. That means average waiting time for 1 customer is 2 minutes. Theta equal to 2. That's what's making it possible to do the chi-square. All right, theta equal to 2. And then what's our alpha? Alpha is we're waiting for 9 customers. So theta equal to 9. R over 2 equal to 9, so the R equal to 18. So if we use a chi-square 18 to do the computation. Any question? Any question? We can definitely use chi-square, use gamma to do the computation. So why do we use chi-square? Simply because we have more resource, we have table. We don't have a chi-square table in the book, and chi-square is less, like, chi-square is more. We have a chi-square table. We don't have a gamma table, right? Gamma table involves two parameters, the alpha and the theta. So normally we would prefer to do chi-square if it's possible. All right. So we want to calculate probability that the x is bigger than 9.39. And the problem waiting for 9 customer is now converted to the total waiting time to be bigger than 0. So we can look at the chi-square distribution table for the degree of freedom equal to 18. Right? So we're gonna pull out the chi-square distribution table, and then the degree of freedom equal to 18. So you can look at rule 18, and then the variable is 9.39. That's in the 0.05. So the probability is 0.05. So the probability to be more than 9.39 is 0. 18 is the average, 9.39 is on the left of the 18. Yeah, so the left side percentage is great. So the right side percentage is 0.005, left side is 0.95. Try to see the left and right. To be more than 9.39 is 0.95. Any question? So you can think of it, the what's being called, you can draw the curve. 18 is the average waiting time for that 9 customers, because we're looking at chi-square 18. 18 is a mean value. So if you have to draw a curve, the center of the curve is at 18, which is a pretty common waiting time for 9 customers. So now we're saying that 9.39 as our waiting time. And we were asking what is the probability to be more than this? We will probably see that's very common, right? Right side to wait more than 9.39. It's a big value there. So from the table, this part is 0.05. So the rest is 0.95. So 0.95. That was. I have to use a little bit of common sense in my head, like what is the mean value compared to the mean value? The 9.39 seems to be a lot smaller than the mean value, which means you're going to find right side percentage is a bigger portion. Any question? Mean is 18, so then you think that is, yes.
I was wondering why it's 18.
Oh, yeah, see, we're saying that the average is 30 customers per hour. If you're waiting for one customer, then 1 hour has 60 minutes, 30 customers per hour. The average waiting time for one customer will be 2 minutes.
Yeah, never mind. I understand.
Yeah, so theta equal to 2, which is why we would want to use chi-square. But in chi-square, the alpha equal to r over 2. But the alpha is the number customer. So alpha is r over 2. R over 2 equal to 9, so r equal to 18. That's why we decided to use r equal to 18 for the chi-square distribution. Any question? Yes.
Can you say again how you got the 0.05 and 0.9?
It's from the table. We have degree freedom equal to 18. That one was okay. So you look at the 18 in the row 18. In the row 18, we find exactly that number 9.39.
Oh, I couldn't see it.
That was yeah. So then we see the chi-square 0.95. That is indicating to the right of 9.39, percentage 0.995. We'll pretty much use a table there. You can also use R. How you use R, you would identify degree freedom equal to 18, right? P chi-square 9.39, degree freedom equal to 18, lower tail false, meaning that we're doing right tail. So right tail is 0.95. That's how you do the calculation with R. The table and R pretty much are giving us the same answer. Any question? It does provide a lot of convenience, but we gotta have to know how to talk to a computer to get a number. You can try yourself, and a couple times trying this, you can start learning how things work. This is the one I use most of the time. I don't have to install anything. That's why in the classroom computer, worry about installing anything. If you run this below here, it comes out. Done by you can even do it on your phone if you want to run a simple R calculation. Okay. So this is another thing about the fact that exponential distribution can also be think of as a chi-square distribution for a special R. So suppose the mean equal to 2 and then R equal to R also equal to. Yeah, you can think of exponential distribution. Exponential distribution, the average waiting time is 2. So you can think of the exponential distribution as a degree freedom equal to 2 chi-square, right? The weight, the mean equal to 2. And for exponential distribution, if the mean time is 2, then exponential distribution is chi-square. If the exponential distribution, the mean is not 2, then it's not chi-square distribution, right? It's special exponential distribution is chi-square, not all of the exponential distribution is chi-square. Any question?
So this is just saying that 2 is just like a special case.
Right. So when the exponential distribution has a mean equal to 2, then it's a special chi-square distribution. All right, so why do we mention this? For the same reason, we do not have exponential distribution table. Not only with the exponential distribution or gamma distribution, we will do our own calculus, we'll do our integration. But in statistics, most people do not like to do, well, even though all the data are from calculus, but they don't want to do they don't want to do the integral all the time. So we rely on the table, and then the table are sources of data. So in statistics, we treat data, solve problems related to data. We want to use data to answer data problems. And all the table are considered our data. So chi-square distribution already have so many tables to go with it. So whenever we can use a table to answer the question, it makes it quicker than have to do extensively calculation or integration So anyway, if you have a question about exponential distribution with mean two, say you want to calculate probability x between those two numbers, then all you have to do is go back to a chi-square distribution table, combine those two numbers, and then you're gonna see your probability. I guess that's something from a table. So degree of freedom number two. Remember that is also exponential distribution. And we're looking for probability for between 0.51, 0.051, and 7.378. So then you can have 0.025, and then you have 0.975. Subtract those two, we're gonna find probability in between. That's any question? So it's just a small mention. I would do my own integration, frankly, whenever it's exponential distribution, I'm fine with integrating the exponential function. It's relatively easier than gamma distributions. So we're gonna try to compare them just so we have a collective view of what's going on. So I have three columns: exponential distribution, gamma distribution, and chi-square distribution. For number one, that we want to know what kind of parameter. Exponential distribution, there's only one parameter, that will be the average waiting time. Gamma distribution has two parameters, average waiting time, and also the how many are you waiting for. And then we have chi-square distribution. The parameter is R, but R is the average, that will be the average waiting time. Other number currently waiting for. Then we have the density function for exponential distribution is e to the, that was wrong. It's 1 over theta, e to the x over theta. That was a bad editing, right? And the gamma distribution density is 1 over the gamma function, theta to the alpha, f to the x to the alpha, is 1 negative x over theta. The chi-square distribution is over here. So when you switch out the alpha to r over 2, switch out theta to 2, you have chi-square distribution. Once you actually put them together, that was not part of it. Once you put them together, you can see their similarity and differences. It's easier to track what it's supposed to do. The mean is theta and variance is theta squared for exponential distribution. Gamma distribution is considered a summation of several exponential distribution. That's why you have off top theta and off top theta squared. There is this underlying additive property between gamma distribution and exponential distribution. The homogeneity function for exponential distribution is 1 over 1 minus theta t. And then here you have that to alpha power. And then for the chi-square distribution, it's the same thing, except alpha is now r over 2. And that's a little hard to remember. Sometimes I have to ask myself, alpha equal to r times 2 or r divided by 2. So if you don't use it for a while, you might have some doubt in your head. Should we multiply or should we add? But keep in mind, alpha is r divided by 2. And the fraction that's involved in r. Any question? And this is another indication that we are actually allowing r to be a fraction, or at least to be half. If r equal to 1, then alpha is 1/2. So it's possible for alpha to be a fraction. And that's kind of the reason that gamma will be more appropriate than the factorial notation. So that's putting all three together, it makes sense. I am adding a few questions from the homework, just for this section because the chapter 3, these three, I have a problem finding out appropriate question from the web work. So I would pick out for just for actual practice. If you want to submit your answer to it, it's on George Review course tool. Simon, this is where you upload your answers. So that way the homework assignment can be also submitted online. The question 9, 18, 21, 23. Any question? The location. I copied those 4 questions down for you, just so you don't have to search in the book. What was it? I guess 13. Section 3.2 homework additional. So in addition to the web work homework, I think I assigned 6 or 7 questions. Two. Those are very basic questions. I feel like not getting enough practice. Those are exponential. All of them are exponential distribution. I cannot find any gamma distribution in the assignment. So I have a couple of chi-square questions, 2 chi-square distribution questions. One, they all multiple choice about chi-square, and then there are a lot of basic questions on exponential distribution. I don't see any gamma distribution. I think that's the reason that I felt like at least the gamma distribution. So that's gamma distribution. This exponential distribution of 21, 23. That's also exponential distribution, frankly. The first two, 18 and number 9, number 18, these are gamma distribution. Number 21 and 23 are exponential distribution. So I pulled 4 questions as additional homework. Any question? That's section 3.2. Some of the very popular continuous distribution. And then the next session we're about to talk about, we only have a few minutes left, is the normal distribution. I'm pretty sure you guys have heard of normal distribution. So normal distribution also has a distribution function that has exponential in there. But we probably gonna focus on these on Wednesday, but at the time. 3.3 is normal distribution. That's it for single variable. And then we're gonna move on to chapter 4 to look at interaction of multiple distribution. Right. What's the normal distribution? It's really a bell-shaped distribution. You have to see it. This is how 2 examples of it. So these are 2 different normal distributions. What's a normal distribution different from the exponential distribution or distribution is symmetrical. We already knew that exponential distribution, gamma distribution, and chi-square distribution, they are non-symmetrical. They're skewed. They're all right skewed, meaning that you have a big tail on the right side, and then on the left side they all start from 0. So that's make them only possible to model situation where that's positive constant, positive number, and you can only model the distribution that's skewed. So the distribution is symmetrical, and if there's no skewness, then we're looking for a better model, and normal distribution will be 1. And if you look at the formula, I have the formula already there. The difference in here is that both of the formula involve e to a negative square term, e to the negative x squared, e to the negative x minus 2 squared. This one, the 2 is the center. That's why you have minus 2 squared. Say having this curve move 2 even to the right. Okay, there's a translation there. So basically, that number controls the center of it. Other than that, it's e to the negative square power. If you compare that with our exponential distribution, we have e to the negative x over theta, right? So in the exponential distribution or normal distribution, e to the x in the exponent of the e is at variable to the power 1. But in the normal distribution, it is e to the negative variable squared. And that's what's the difference. The difference is this function, they're symmetrical. On the left and on the right of the center, it's symmetrical. But that exponent e to the negative exponent over the function skews to the right. The large tail, and then the exponential function made it only possible for x to be positive number, if X negative number function is not well defined. Anyway, so here we are. Dr. Tommy look with this. And, gonna talk about more on normal distribution. We actually have a quicker way to handle normal distribution. This is the most popular continuous distribution. If you have heard of it, you probably had a lot of things like normal distribution table, right? Standardized normal distribution. Yeah, so we're gonna come back to it on Wednesday. That'll be after 2. Thank you.